In this segment, we'll talk about introduction to binary representation of numbers. In everyday life, we use number systems that have a base 10, also called the decimal numeral system. And when a number is written in this system, we can quickly decipher as what those numbers really mean. So for example, if I take a number like 267.35, I know exactly that, hey, this 267 and 0.35 is the number, and we don't think too much about it. But what you got to understand is that each of these numbers have a place. So for example, this one is the place for hundreds. This one is place for the tens. This one is the place for ones. And then after the decimal point, this place is for 1/10, that's 10 power minus 1, and this place is for 100ths. So if we had to write 267.35, we would also be able to write it as 2 times 10 to the power 2 plus 6 times 10 to the power 1 plus 7 times 10 to the power 0. And then for the fractional part, which is this one right here, we'll say 3 times 10 to the power minus 1 plus 5 times 10 to the power minus 2. So you can see that how if we expand this number, we'll get 200 plus 60 plus 7 plus 0.3 plus 0.05, and eventually we'll get back our number of 267.35. So the binary system is not any different. The only difference is that the base is different. The base is only 2. So the only numbers which you can have are zeros and ones so far as the digits are concerned. In base 10, we know that the digits which we can have is any number from 0 through 9. We have 10 different digits. But for binary, it will be base 2, so we can have only 2 digits in it, and those 2 digits are 0 and 1. Let's go and see that what that means. So let's look at a number in base 2. So a number like this, for example. Now what's going to happen is that this is base 2 number, so there's only going to be ones and zeros in the number. This dot here is called the radix point. It is no longer called the decimal point because the decimal point only is connected to the decimal numeral system. And then of course this is called the fractional part, and this is called the integer part of the number. But what's now different is only this fact that, hey, let's suppose if you look at this number 1 here, this is corresponding to the power 0. The place for this one is 2 to the power 1. So just the base is different. This is 2 to the power 2, and this place here is 2 to the power 3. And if you look at this one, this is 2 to the power minus 1. This place is 2 to the power minus 2. And this place is 2 to the power minus 3. And this place here is 2 to the power minus 4. So only the base is different. Everything else is still the same. So let's suppose somebody says, hey, can you tell me what the equivalent of this number is in base 10? It'll be just equal to 1 times 2 to the power 3 plus 1 times 2 to the power 2 plus 0 times 2 to the power 1 plus 1 times 2 to the power 0. Because this is 1 times 2 to the power 3, 1 times 2 to the power 2, 0 times 2 to the power 1, 1 times 2 to the power 0. Then let's look at the fractional part. It will be 1 times 2 to the power minus 1 plus 0 times 2 to the power minus 2 plus 1 times 2 to the power minus 3 plus 1 times 2 to the power minus 4. 1 times 2 to the power minus 1, 0 times 2 to the power minus 2, 1 times 2 to the power minus 3, and 1 times 2 to the power minus 4. So if we expand this, we get 8 from the first one, then we get 4, then we get 0, and then we get 1. And then from the fractional part, which is this part right here, we get 0.5, we get 0, we get 0.125, and then from here we get 0.0625. That's what we get here. So now if we're going to add these numbers, we'll get 13 from here, right? And then we will get 13.0, no, not 0, 13.6875. That'll be equivalent to the base 10. And so once we have realized that, we can now convert a base 2 number to base 10 number, and that tells you that how the equivalency there is. In the next lesson, we'll talk about the reverse. How do we convert a base 10 number to a base 2 number? And that is the end of this segment.